All right, so this little talk is about how to do capacitors in series and in parallel. So when you have circuit setups, okay? So to start off with, hey, you got a capacitor connected across a battery 5 volts. Additional capacity 2 is connected across a battery of 10 volts. Which one has more charge? Your answer is 2, because if you double the voltage in the same kind of capacitor, you can put twice as much charge. Remember, capacitor is charge per volt. You double the voltage, you get twice the charge. You're not physically changing the capacitor, you're not changing the area or how close the plates are or what's in the middle of those things, so the capacitance will remain the same. But the one that have more charge is the C2. Alrighty, hey, another great question. What has to be done to increase the amount of charge that the capacitor can hold for a constant voltage? So higher voltage pushes more charge onto here. But the other way is to, which of these? Well, if you increase the area, can you put more charge on there? Yes, because you got more space. They don't push on each other as hard if you have more area. How about if you decrease the separation? Well, if you decrease the separation, now they tug on each other. And if they tug on each other, there's actually more room to put even more charge onto there. So 2 actually works. Decrease the area. Now that's less room. That squishes the charge together. That pushes harder on each other, and you can't put as much on there. So the answer is indeed number 4. Alrighty, so here we go in series and parallel. Now here we have a parallel setup. It's parallel because we have the same potential on each side and the same potential difference across on these capacitors. So the advantage of a parallel setup is an increased capacitance, because look what you're doing. If these are the exact same capacitors, this is double the area. Now this is triple the area. If you have triple the area, you literally have 3 times the capacitance, or 3 times the charge you can store per volt. So to find the total capacitance in parallel, you just add them up. Couldn't be easier. But what's the same everywhere is the potential, because you have the same, you're hooked to the same side on the battery in each case. Okay, so then by hooking capacitors up in parallel, it's a good way to store energy. So in case you hook up another circuit to the A and the B, if for some reason it needs a lot of charge all of a sudden, and the battery can, remember, it can only deliver charges so quickly out of the battery. So because of that, a capacitor bank in parallel can deliver an extra needed charge very quickly. Oh, so what? How do you find the total charge? Add all 3 up. I don't have that on here. But to find the total charge, that charge plus that charge plus that charge, that's the total charge. Hey, how about the series? So the series actually doesn't make it easier to store charge. It makes it harder to store charge. Reason is, if let's say you've put 11 electrons shoving on this plate. Well, that shoves 11 electrons that way. That shoves 11 electrons that way. That shoves 11 electrons back over around to the side over here. So you have the same exact charge on every single capacitor. So in a series, the charge is going to be the same. Okay? Because if you were to double the charge on this side, that pushes twice as much there, twice as much there, twice as much there. But you can't add them up and have 3 times the charge, because you only have that amount of charge moved from one plate to another. Keep in mind, there's no charges jumping between the plates. There's a disconnect there. So it's a dielectric. If it does go through there, you're burning a hole, and it's no longer the same capacitance it was anymore. Okay, so no charges are actually jumping the gap here. I'm putting 11 there, that pushes 11 there, that pushes 11 over there, and that pushes 11 back this direction in terms of electrons. So you don't actually store. In fact, your capacitance decreases because you have an extra field every time you add one. Your capacitance actually decreases. So this is how we find the total capacitance in series. Now, because of that, you're going to get a voltage drop across each one of these. Now, if they're the same capacitors, it's an equal voltage drop. But if they're not, it won't be, but they're still going to sum up to be the total. Okay, so here we go. Now we have this combo. We have a parallel, 2 and 3, and a series with the 1. So the first step is to make it all parallel or all series. Well, it looks like to me the easiest thing is going to be make this all series. So I'm going to start off making that a parallel. Okay, so we're going to put those in. So that plus that equals the total. So not the total, but this is the total capacitance right here. So I'm making a combo. I'm making a combo of the 2 and 3 into a 1 called C23, and that's my combination, which is in a series with that one. So remember, it's going to be a 3 and a 3 in parallel with a 3 in series. But still, we're going to treat it as a single one. Okay? So that's my combo. So next what we're going to do is we're going to find the total capacitance. They can find their charge and everything else. So to find the total capacitance, well, that's a series, right? But first, this was a parallel, if you remember. I got to do the parallel first. The parallel is easy. C2 plus C3, so that's 3 plus 3 is 6. So this is actually a 6 microfarad equivalent capacitance, whereas this is still a 3. Since these are in series, I got to do my 1 over 6, that's my 2, 3 right here, and my 1 over 3, which is 2, 6, that's my C1. So that's 3, 6, but that's 1 over the total capacitance is 3, 6. So you invert that, it's actually the total capacitance is 2 microfarads. It's decreased lower than the 3. Okay, so by having it in series, I actually decrease my total capacitance because now we got 2 electric fields there as a model. Okay, next I got to find my volts across here. So across everything is 4, but one of these is going to have a bigger drop than the other. Which do you think it might be? Well, let's start with the total charge first. Total charge is the total capacitance times the total voltage. So we just found it's 2 microfarads over here, times your total voltage drop 4, 8 microcoulombs. So the entire circuit that's a parallel plus the series together is storing a total of 8 microcoulombs. Now remember, it's the same charge here as it is here. So that means across 2, 3, we also have 8 microcoulombs of charge stored. But let's back up and find the voltage drop across the C1. So voltage drop is the charge per capacitance. And the charge we just found is 8 microcoulombs divided by its capacitance 3. It's a 2.67 volt drop across there. Do the same thing with the 2, 3. It's an 8 microcoulomb total charge stored there. Remember, it's the same in series. So that's an 8 there, but divided by the combo 6 microfarads, that's a 1.33 volts. And those two add up to be 4. So everything is hunky-dory so far. Okay? So now we have the voltage drop across this. We have the charge stored on there as 8. We have the capacitance. Now we got to separate these two back out. Okay, so separating those two back out, if you remember, the voltage drop across here is 2.67, but across here it's 1.33. So that's since we know the capacitance of each one is 3, now we just solve for the charge stored onto there. So capacitance is 3 times the voltage, 1.33. It's 4 microcoulombs. And on the next one, wait for it, also 4 microcoulombs because of the same type of capacitor. And 4 plus 4 is 8. So just like we said earlier, we had a combo of 8 stored right over here and 8 stored over here. That doesn't mean we have 16. We can't get 16 out of it, because if you only put 16 electrons over there, we can only get 16 electrons to come back across over here. Okay, so that's not 8 plus 8 is 16. The total charge stored is 8, which is also 8 there as well. Okay, alrighty. So little quick comprehensive test here. Hey, we got a series and a parallel. Which are which? Series in parallel with this one. So you got to do your series rule here, the 1 over the C, 1 over the C, and then you can add that value to the C. When you're all done, which one is it? Take some time. Well, we don't have all day, so bam. I guess you could have paused it before I said bam. I didn't give you a warning. My bad. It's 3/2 C. So you can go and verify that on your own. Okay. Alrighty. One last problem here. Parallel plate capacitor carries a charge Q disconnected from the battery. The two plates are initially separated by D. Suppose those plates are pulled apart till it's 2D. How has the energy stored in this? How has the energy stored in the capacitor changed? I'm going to give you a couple minutes here. No, not 2 minutes, because I got other stuff I got to do. I got a recorder lesson I got to do today. Families learning how to do recorders. Woohoo! It's different. Or pause for a moment, figure it out yourself, because I'm going to keep on rolling. Alrighty. So it doubles. Okay? So here's why it doubles. We're not changing the charge, but what happens is we're not changing the area, not changing the epsilon or the permittivity, whatever's on the inside of this thing. We're changing the distance. And so since these are the only two things in our equation we're changing is this and this, they're directly proportional to each other. Twice the distance is twice the potential. So the reason the potential goes up, because as the plates get further apart, the charges on each plate are pushing harder on each other. They're not attracting each other here as hard. Now they're shoving each other harder. The potential actually increases. And think about it. If I want to lift a calculator up from the earth, it takes work to pull that apart. It increases in potential energy. Same thing with capacitor plates. They're oppositely charged. I'm pulling them apart. It takes work to do that. I'm actually storing potential energy as I pull those things apart. Okay? So since the potential doubles, the charge stays the same. That actually doubles the potential energy. Sure, the capacitance is half. That cuts the capacitance in half. But even by this, half capacitance, twice the voltage, that's 2 times 4 is 4 divided by the 2. It all works out the same. So it's actually twice the energy if you pull those things apart. So what do you use these things for? All kinds of things. Stored energy normally, because they can deliver energy faster than what a battery can do. A battery can deliver energy into a system, but because chemical potential energy, this is electric potential energy, capacitors can be much faster. So if you need a large charge across somebody's heart to get it working again, to jolt it going, you have a nice sized capacitor in there that gets charged up over time. Then you're ready, hit the button, and bam, it delivers across there rather quickly a large amount of charge to get that thing going. All right, well, I hope that helps with everything. Talk to you later.